Like the majority of the systems on the A320, the air conditioning system is fully automatic and is designed to provide a comfortable atmosphere in which to work and travel. We will begin our study of the system by first looking at the air conditioning packs. The A320 is equipped with two air conditioning packs located in the wing root area forward of the landing gear bay. Let's look at how a pack works. Hot bleed air enters the pack via a pack flow control valve. The purpose of this valve is to adjust the flow rate through the pack. The air then passes through several stages within the pack that progressively cool the air to provide a conditioned air output. Sub-zero temperatures can be achieved. Two of the stages are heat exchangers that use a flow of ambient air over them to cool the hot bleed air. This flow of air enters via a pack inlet scoop and exits via an outlet duct. So that the output temperature of the pack can be adjusted, a bypass valve is fitted. This valve allows warmer air to be mixed with the cold air. The pack flow control valve and the bypass valve are regulated by a pack controller to vary the flow rate and the output temperature. The pack controller also controls the inlet scoop and outlet duct to vary the amount of air passing over the heat exchangers. Note, to avoid ingestion of foreign matter, the inlet scoop and outlet duct close temporarily during takeoff and landing. To make things simpler, let's define the area within the yellow box as a pack. The two air conditioning packs operate automatically and independently to provide cool conditioned air. The conditioned air from the packs is then fed to a mixing unit. In case of failure of both packs, ram air is provided via a ram air valve. We will look at the use of ram air in the abnormal operation module. Various pack parameters are monitored by ECAM. They are pack flow, compressor outlet temperature, bypass valve position, pack outlet temperature. These parameters, along with the valve positions, are displayed on the upper part of the ECAM bleed page. Having discussed the air conditioning packs, we will now look at how temperature and flow regulation is achieved throughout the aircraft. The three outputs from the mixing unit feed three separate aircraft zones: cockpit, forward cabin, and aft cabin. Let's look at how the temperature of the zones is managed. A zone control computer monitors the temperatures of the three zones and sends signals to the pack controllers to set the air temperature delivered by the packs. Normally, cold air is delivered by the packs and is then sent to the three zones. Since the different areas of the aircraft may require different amounts of cooling or heating, hot bleed air can be added via trim air valves to obtain the demanded temperature for a zone. In the example shown, no hot air is being added to the cockpit zone. Some hot air is being added to the forward cabin zone, and a lot of hot air is being added to the aft cabin zone. The trim air valves are supplied via a hot air valve. The purpose of this valve is to regulate the pressure of the hot air supplied to the trim system and to act as a shut-off valve. The hot bleed air is supplied to the hot air valve downstream of the pack flow valves. This means that if the pack flow valves are closed, there is no air supplied to the trim system. The hot air valve and the trim air valves will automatically close. The trim air valves and the hot air valve are controlled by the zone control computer. Zone duct temperature, which is the temperature of the air entering a zone, and the actual zone temperature are monitored by the zone control computer and presented on ECAM. The ECAM COND page contains zone temperature and trim air system indications. The ECAM cruise page also contains zone temperature indications. On the overhead panel, the air conditioning panel allows the pilots to control the air conditioning system. Let's look at this control in detail. The pack push-button switches control their associated pack flow control valves. In this example, pack 1 push-button switch is selected off. The corresponding valve is closed. Pack 2 push-button switch is selected on. The corresponding valve is open. The pack flow selector permits selection of the desired pack flow. We will look at the use of this selector in more detail during the normal operation module. The guarded ram air push-button switch controls the ram air valve. In the example shown, the ram air valve is closed. The use of this push-button switch is restricted to abnormal conditions that will be discussed later. The hot air push-button switch is associated with the hot air valve. In the example shown, the valve is open. Now let's look at the temperature control. The zone temperature selectors are used to adjust the required temperature for an associated zone. 2 cabin fans are fitted to reduce the bleed air requirement and therefore save fuel. These fans establish a recirculation flow of air from the 3 aircraft zones to the mixing unit. In normal operation, there are no ECAM indications associated with the cabin fans. The cabin fans push-button switch on the ventilation panel controls the cabin fans. This push-button switch can be used to switch the fans off in response to ECAM procedure. We will look at using the air conditioning system during a normal flight. As part of the aircraft walk-around, check that the pack inlet and outlet areas are clear of debris and the ram air valve is closed. Let's assume that you are about to start the flight. The APU is running and you require air conditioning. You are now in the cockpit, and this is how you find the air conditioning panel during your scanning sequence. Notice that, except for the off lights on the 2 pack push-button switches, all other push-buttons are in the normal lights out position. One of the items in the cockpit pre-flight check is to extinguish all white lights on the overhead panel. So that you can watch what is happening, let's have a look at the ECAM bleed page. Call the ECAM bleed page. Switch pack 1 to on. Notice the amber fault light on the pack 1 push-button switch. The control valve indication switching from green to amber. Both of these amber indications occur because pack 1 is on, but no bleed air is available to it. Switch pack 2 on. As for pack 1, notice the amber fault light on the pack 2 push-button switch. The control valve indication changes from green to amber. As before, there is no available bleed air to pack 2. Since you are expecting a standard passenger load, the pack flow selector can be selected to normal. Set pack flow to normal. There are no changes to the ECAM indications. The pack flow selector only affects the pack flow rate once the engines are running and supplying bleed air to the packs. We will look at the use of the pack flow selector later in this module. It is now time to get some air to the packs. As the APU is already running, set the APU bleed to on and watch the ECAM indications. Switch APU bleed to on. Notice the APU valve indication has changed to inline green. The cross-bleed valve has automatically opened. Notice the cross-bleed selector is in the auto position. Both feed lines to the packs have been connected. Let's now look at the packs. Notice the fault lights are extinguished due to the air supply. The pack flow valves are open. The pack flows increase. The bypass valves move. The supply lines to the mixing unit are now connected. Both packs are now providing air conditioning. Let's look at temperature regulation of the air conditioning system. This is better seen on the ECAM COND page. Call the ECAM COND page. Let us concentrate on the upper part of the ECAM COND page. Look carefully at the indications. Notice in particular the zone temperatures and the duct inlet temperatures. Temperature regulation is achieved the same way for all zones. We will demonstrate the concept using the cockpit zone as an example. The cockpit zone temperature selector is in the 12 o'clock position. In this position, a zone temperature of approximately 24 degrees Celsius is demanded. As the 15 degrees Celsius of the cockpit zone is well below the demanded 24 degrees, the zone controller sends a command to increase the amount of hot air to be added. Due to this command, the trim air valve opens. The zone duct temperature increases, and so warm air is supplied to the cockpit zone, and the cockpit zone starts to warm up. Once the cockpit zone reaches the demanded temperature, the trim air valve will move, reducing the amount of hot air, and then will move as required to maintain the zone temperature. It is now time to start the engines. So that you can watch what is happening, let's go back to the ECAM bleed page. Note, normally the engine page is displayed during engine start. For training purposes, we will display the bleed page. Call the ECAM bleed page. Let's start the engines. Be sure to watch the pack valves on the ECAM bleed page. Click on either engine. As soon as the engine start sequence begins, the pack valves close. This is so that all of the APU bleed air can be used to start the engines. Let's complete the sequence. When the engine starting sequence is completed, the pack valves open and the APU bleed supplies the packs. Notice that the engine bleed valves are closed, even with both engines running. This is because APU bleed has priority over the engine bleed. So, if you are departing from a performance limited runway, the packs could run from the APU bleed air, resulting in no loss of engine performance, no weight penalty. However, today, in our example, the APU is no longer required. Switch off the APU bleed. Off. Both engine bleed valves open, supplying the packs with bleed air. The APU bleed and cross bleed valves close, and the link lines disappear. Notice that the pack flow reduces. This is because the engines provide a higher flow rate than the APU. Also note that the air conditioning control panel is now in a normal lights-out configuration. When the APU is shut down, the APU symbol on the bleed page is removed. During the flight phase, the air conditioning system will work automatically, and the only likely pilot input that may be required is to adjust zone temperature. Let us assume that you wish to cool down the cockpit. To demonstrate, please select the cockpit zone selector to cold. You have now demanded a cockpit zone temperature of 18 degrees. Because a low temperature has been demanded, the trim air valve will close and the cool pack output will feed the cockpit zone. Note that each increment on the zone temperature selector scale is 2 degrees, which gives a selectable range from 18 degrees at cold to 30 degrees at hot. In situations of low passenger numbers, the pack flow selector can be set to low. This has the effect of reducing the bleed demand from the engines and will therefore save fuel. Occasionally, with a full passenger load and high ambient temperatures, it may be necessary to select high pack flow and cold to reduce the cabin temperature. Using high pack flow will increase the bleed demand from the engines and use more fuel. Once airborne, the flow selector should be returned to normal and the temperature selectors adjusted as required. After landing and engine shutdown, the system can be set to run from the APU or switched off completely. An external conditioning unit can also be connected via a low-pressure connection point on the underside of the aircraft. The low-pressure air is fed to the mixing unit and then into the 3 zones. There are no indications in the cockpit to show that an external conditioning unit is in use. Demonstration of an in-flight pack overheat. You are the pilot non-flying. You are currently flying at your cruise flight level. Everything is normal. Let's look at the indications. A failure message and associated ECAM procedure have appeared on the engine warning display. The ECAM bleed page has been automatically called to show amber indications, and a fault light has illuminated on the air conditioning control panel. On the engine warning display, read the title of the failure. Before you begin, notice that the pack flow control valve has closed. This occurred automatically when the overheat was detected to protect the pack from damage. The valve color indication is amber because the valve position disagrees with the push-button switch position. The compressor outlet temperature is also amber because its limit has been exceeded. Notice also that since the pack valve has closed, the supply line from the pack to the mixer unit has turned amber. This happened because there is no airflow from the pack to the mixing unit. The pilot flying will ask you to perform the ECAM actions. You, as pilot non-flying, read and perform the ECAM actions. The first step on ECAM directs you to turn off pack 1. This is to match pack push-button switch and pack valve position and prepare to reset the pack. Note that the fault light on the pack push-button switch is illuminated to help you locate it and to indicate the overheat condition. Switch off pack 1. When pack 1 is turned off, an off light illuminates in the switch, and the pack valve indication turns green, showing valve switch agreement. Notice that the fault light is still illuminated. The completed procedural step disappears from the engine warning display. The compressor outlet temperature is now decreasing. Let's move on to the next step of the procedure. The first part is not an action, but a condition line. We are to determine if the pack overheat is out. The fault light in the switch is extinguished, and the compressor outlet temperature indication is green, so we can conclude that the overheat is out. Therefore, Accomplish the next ECAM action by switching pack 1 back on. Switch on pack 1. When the pack switch is switched back on, the off light is extinguished, normal memos replace the failure message on the engine warning display because the failure condition no longer exists, and the cruise page returns to the system display. You have now completed the ECAM actions. The pack overheat condition has gone and the pack is reset. This is an example of an abnormal procedure. We will use a trim air system fault to illustrate these procedures. You are in cruise and all the systems are functioning normally. You are the pilot non-flying. When the ECAM system detects a failure, the appropriate alerts are generated and the system screen called up. Because this is only a crew awareness, neither the master caution nor the master warning lights illuminate. You are the pilot non-flying and you have the task of performing the ECAM actions. The failure message is Conditioning Trim Air System Fault. The ECAM procedures are now followed. In the case of a trim air system fault, there is no action required by the crew. The next step in this example, after checking with the other pilot, is to clear ECAM. Clear ECAM. Because this was just a crew awareness and no action was required by the crew, no status page is displayed. The cruise page is now displayed and the clear lights are out. The ECAM procedure for a trim air fault is complete. Now let's look at some other abnormal indications associated with the air conditioning system. If an ECAM or QRH procedure requires the use of the ram air switch, it is operated by lifting the guarded flap and pushing the switch. Select the ram air switch. An on light illuminates in the switch. The valve will open and the indication on the ECAM bleed page will change to show this. Note, according to ECAM procedures, normally the aircraft must be below flight level 100 minimum en route altitude to operate the ram air valve, as the aircraft will depressurize. Let's look at another abnormal indication. The hot air fault light illuminates amber when a duct overheat is detected. If this occurs, the hot air pressure regulating valve and the trim air valves automatically close. If a fault in a cabin recirculation fan is detected, the cabin fan indication is displayed in amber. The zone control computer, with 2 channels, normally operates without any indications to the pilots. However, if a fault occurs, there are backup modes of operation with associated indications. In the first case, if a primary channel failure occurs, the secondary channel takes over, and optimized temperature regulation is lost. An alternate mode message appears, and the hot air and trim air valves close. On the status page, you are advised that the cabin zone is at a fixed temperature. In the second case, if a dual channel failure occurs, there is no zone temperature regulation. The packs deliver a fixed temperature and the message Pack Reg appears on the ECAM conditioning page. Notice also that there are no indications of zone or duct temperature. On the status page, you are advised that the packs are delivering air at a fixed temperature. The conditioning of the air in the two cargo compartments is fully automatic. The operation for both compartments is similar, so we will only look at the forward cargo compartment initially. Ambient air from the cabin area enters the cargo compartment via an inlet isolation valve. The air is removed from the compartment either by an extractor fan or by differential pressure. The air is discharged overboard via an outlet isolation valve. The operation of the two isolation valves and the extraction fan is controlled automatically by a cargo ventilation controller. To provide heating of the cargo compartment, hot bleed air is supplied via a trim air valve. The operation of the cargo trim air system is very similar to the trim air system for the air conditioning system. Each cargo compartment has a cargo heating controller, which controls the trim air valve position to regulate the temperature of the compartment. Let's look at the ECAM conditioning page to see how information on the cargo conditioning system is presented to the pilots. The cargo heating system is an extension of the air conditioning system. Hot air is routed from the trim air system for the forward cargo hold and via an independent hot air valve for the aft cargo hold. On the ECAM conditioning page, the indications associated with the cargo compartments are the isolation valves, the trim air valves, the duct inlet temperature, the compartment temperature, and the aft cargo hot air valve. Notice that there are no indications for the extractor fans. On the overhead panel, there is a cargo heat panel, which contains the controls associated with cargo heating and conditioning. For each cargo compartment, there is an isolation valve push-button switch. These push-button switches normally remain in their lights-out auto position. In this case, the cargo ventilation controller will automatically open and close the isolation valves. The temperature selectors send demand signals to the associated cargo heating controllers. The cargo heating controllers then move the trim air valves to adjust the temperature of the air entering the compartment. The hot air push-button switch controls the aft cargo compartment hot air valve via the aft cargo heating controller. This push-button switch normally remains in the lights-out auto position. Notice that the forward cargo compartment does not have an independent hot air valve. The forward cargo trim air system is fed from the cabin hot air valve. For normal operation of the cargo conditioning system, the only pilot inputs required are to confirm that the push-button switches are in their normal lights-out position and to set the required temperatures. Note that the mid-position of the temperature selector is approximately 16 degrees Celsius. The abnormal operation of the system is very similar to those already seen in the air conditioning abnormal modules.